This is Daly from Intel. Nadav, Liron, you want to introduce as well while I pull up the slides?
Yeah, hi. So I'm Nadav from Marvell. In Marvell, I'm running a group of engineers looking into accelerating different networking applications using the Marvell Octane DPU. My team is mainly focused on virtual networking, different use cases of OVS offload, and also looking into DPU acceleration of security offload, such as TLS, KTLS, and so on. And maybe I can also introduce Liron for my team, who's leading the virtual networking and OVS offload efforts.
Hi, everybody.
Okay. So I think in all the previous presentations, I think that we've well established this slide. So, there's clearly a need here for these types of programmable devices within our programmable infrastructure. So I'm not going to spend too much time on here. What we want in this session is to be able to, we're going to start by showing you a little demo that kind of shows a target working with the existing abstractions that we have today inside of IPDK. And then we want to open this session up to discussion. We'll see how this goes, enable everyone's mics, and we can continue to use the chat to bring questions, or we can have people just jump in, raise hands. We'll see how this goes as our first breakout of OPI alpha. So, what we're really seeing as the challenges from the previous meetings is, we have yet to agree upon a set of standards that we feel are, not only sort of used across the industry, but also effective. It's one thing to have a standard. It's another thing to have a standard that has the right performance, is robust, and is sort of widely accepted. And secondly, we have all of these new devices emerging, and not only just new devices, but also those devices have new hardware accelerators, new hardware capabilities that need to be programmed. And so, given this set of challenges, this is what I think we're all here to talk about in these last few days. And what we want to do is talk about specifically how we get to that sort of the bottom of the stack and be able to support all those different types of devices there in the picture, and be able to do it in a sort of in a consistent, cohesive fashion. So I'm gonna pass to Marvell team, and they're going to show you an example.
Yeah, great, thanks, Dan. I think we can jump to the next slide. Yeah, so in the coming slides, we'll be looking at some real life example and some POC that we have been doing recently with the IPDK project and the Octane DPU. Therefore, we thought it may be interesting to say maybe first few words about the Marvell's latest DPUs, for those who are not yet familiar with them. So in a nutshell, without getting all the details, Marvell's latest DPUs are 5 nanometer silicon devices. They include CPUs that are based on ARM's latest Neoverse family. In addition, they offer dedicated IPs for security acceleration, such as TLS, IPsec, and also machine learning IPs. So those are pretty strong machines on their own, capable of running latest distros such as RHEL, virtual machines, heavy containers, and so on. The Fusion Octane DPU family is targeting the O1 and VRAM space with its dedicated 5G layer L1 functionality. Yeah, we can go to the next one. So in Marvell, we strive to expose and unleash the features of our hardware through standardized software. I believe this works for both Marvell as a hardware vendor, who can focus primarily on optimizing its silicon, and also for customers when integrating and evaluating our products. In the DPU space, we've been engaged with different standardization paths, starting from the Diamond Bluff initiative, where one of the early members and actively contributing in the different subgroups In addition, we recently proposed a new standard framework for DPUs as part of the DPDK project, which we named the Data Plane Workload Accelerator, DWA. The RFC just got accepted, and we're working these days on submission of the first profile. With OpenShift, we ramp up the interesting DPU mode that was mentioned in the previous Red Hat lecture. We have a bit different path with we based on DPDK, unlike what was mentioned there. And lastly, we had a recent experience with the IPDK projects that we'll be sharing with you in the coming slides. So Liron, I think you can go ahead.
Yeah, thank you, Nadav. Yeah, okay. So one of the main goals of the DPU is to offload an entire network stack, including its control plane. Oh no, not yet, thanks. Okay, so today we will focus on OVS offload to a Marvell DPU and the exploration that was done with P4 OVS in IPDK environment. Next, please. So what OVS offload means? It means that all OVS services are running on a DPU cores. In terms of the host, the entire OVS is offloaded to the DPU, but the actual data path flows are either processed by the DPU cores or by the DPU hardware, which is of course the most desired option to gain optimal results. It provides full connectivity between host and DPU containers, which can also be used for service chaining functionality. Next, please. So here we can see OVS offload use case as it's supported by Marvell DPU. In a typical use case, the OVS and the containers are both running on the host cores. But as part of the infrastructure offload, we offloaded the OVS from the host to the DPU ARM cores. In addition, as was said before, Marvell DPU contains powerful ARM cores. So containers can also be offloaded from the host to the DPU cores. And finally, by offloading the OVS flows to the hardware, we can gain optimal connectivity between all the containers, those on the host and those on the DPU. Okay, next, please. So now we will describe the DPU POC we did using IPDK. The motivation was to explore P4-based solution for the Octon DPU family. And we found out that the IPDK looks like a good candidate to be used for that. The general goal for this POC is to run a DPU use case with P4 OVS in an IPDK environment. Next, please. So we started with IPDK running on Octon ARM cores. Basically, we took the IPDK demo as it's running on a host and duplicate it on ARM platform. IPDK demo contains P4 OVS, which runs the P4 application with a P4 DPDK target as a default P4 target. It exposes virt.io interfaces that in this case attach to our virtual machines on the DPU and forwarding the traffic. In this step of the POC, we also solved some of the ARM integration issues and upstreamed them to the community. Next, please. So once we had the basic IPDK demo running on the Octon, we moved to a DPU mode. In this mode, the virtual machines are running on the host cores and attached to Octon virtual functions. In Octon, all embedded interfaces are PCI interfaces. So we had to add a DPDK bridge application to connect our SDP PCI, which is actually a VF representer interface on the Octon side, with the virt.io interfaces, which is the only supported interface type in the current IPDK. So after we connected all the dots, we could now forward traffic between the virtual functions, virtual machines on the host using the P4 OVS on the DPU side. And we can also do some performance measurements based on the P4 DPDK target, which is a software-based P4 target. We also had a demo, but we didn't want to waste time in this session. So we will upload that to the YouTube and we'll share the link later on. So to conclude, here are a list of findings we want to share. IPDK was working very smoothly on Octane DPU, but just after we fixed the ARM support. We also found that the P4 DPDK target has some performance limitation, in particular with CPU scalability, which currently only one core is supported. And as mentioned before, only VirtIO is supported. But PCI device is very critical for Marvell, as our external interfaces and the DPU host interfaces are all PCI interfaces. So thank you, and back to you, Dan.
Cool, thank you. Yeah, and we'll put that the demo up in the with all the other videos that we're going to have from these three presentations. And so I think that that's a really good example of how you took something that was built to abstract a set of Intel targets and was able to run it and make the necessary modifications to run it on your target, and then brought back the patches and the changes that you found, and we put them back into the code base for P4 OVS. And so now that we have that, we have to think about how do we abstract these different targets so that where there's consistency, we have a standard for exporting that functionality to the application above. And at the same time, being able to support the full range of functionality. If sort of VirtIO is not supported or fast enough in the environment, how do we get other types of interfaces in there? If a P4 DPDK pipeline in software is not fast enough, then how do we integrate that with the other capabilities that are in the platform? And we want to do this in a way that doesn't obfuscate what's underneath and inside the target. We also don't want to do it in a way that favors one implementation over the other. And in this breakout, we would love to solicit feedback as to sort of how do we move forward with this abstraction. How do we organize ourselves to be able to get all of these different devices running with each other's code and try to work out some of these issues that are going to keep popping up as we start bringing up all these different environments. Let's see. I think we were going to try out enabling. Or actually, Susan, I'll defer to you. What is our format that we want to try for the breakout session?
We would love to have people chatting with you and just asking questions verbally if they can unmute. We are still not sure if we've done that properly. So if somebody wants to start talking, that would be great. Otherwise, while we're figuring that out, please go ahead and use the chat window.
Okay, great.
All right, well, I came off mute. Can you hear me?
Yeah.
Yes.
Great.
Excellent.
All right, it's working.
Cool. Yeah, so
I'll kick off a question, Dan.
Great.
What if a vendor doesn't want to embrace P4? What if that's not what they want to use? What are their options to work within IPDK?
Yeah, so inside of IPDK, we have a device that we've been testing that doesn't immediately run P4 in a hardware pipeline. And so we're able to run the P4 pipeline using P4 to BDK. And so we can also run the P4 pipeline. So that's a software implementation of the P4 pipeline. We're also working on a pipeline that uses eBPF with a partner. And we have slides in this deck, just in case we ran out of questions, to talk more about Marvell's exploration of using eBPF on the platform. So the default here inside of IPDK is to make sure that, you know, if you have a pipeline, that we can always run everything in software. And there's always a place where you can run everything in IPDK without having any special hardware.
Just to tag on to that question, I think there's a class of problems for which I think P4 is an excellent solution, and doing it in other ways is very difficult. But do you see a class of problems that don't lend themselves to being P4 programmable?
Oh, absolutely.
And
yeah.
what would be our approach for targeting that in the IPDK framework?
The easiest example is storage. So inside of IPDK, all of the storage is rooted inside of SPDK. And there's no P4 inside of that system per se, other than when the SPDK goes and uses the network. So another area is crypto, where there's, you know, there may be a look-aside device, or there may be a piece of logic that's hanging off of the course that is really not necessary to loop into the P4 environment. There's inline accelerations that can fit really nicely, and we've added some of those abstractions in the PNA architecture. But you know, if IPDK is sort of a little toolbox that we're building, and we're pulling open source, you know, components into it, pulled in P4 for some of the networking pieces. It's also really useful for some of the Kubernetes and Envoy pieces. But there's all sorts of other things that need to be added as well. It's just really one part of the picture. Rob, you have a handout?
I have obnoxiously raised my hand. We'll see if this works.
Yeah.
I think, you know, until you kind of get down into the nuts and bolts of what it means to program these things, it becomes like, until you do that, like you could say, okay, well, IPDK is P4 and P4 doesn't solve everything. So obviously IPDK is limited, right? But if you get down to the nuts and bolts of it, you know, I think the previous question was really just the tip of the iceberg. You need, you know, an API to manage VFs and PFs. You need an API to efficiently transfer data between the host and, you know, the IPU, DPU. You need storage primitives. You need primitives that abstract the various accelerators. And I think, you know, for its value, P4 is great at modeling a switch pipeline, which for most of these devices, there's a component which is a switch pipeline. And I think it's easy to point out that, okay, you know, that's where we have running code. That must be the main focus. But I think the reality is that we're going to have kind of a piecemeal collection of recipes for, if you want to use this piece, you have these APIs. You want to use this piece, you have these APIs. And that whole thing will be the OPI infrastructure. And just P4 is, I think, one of many components there, is how I think about it. And by the way, I think ultimately an optional component, you know, I continue to have arguments with people about P4 versus ABPF versus DPDK versus something else. And those are great. And I think we want to encourage those. So yeah, anyways.
I think a comment that was made earlier was, you know, it is definitely directly from our experience was, you know, come in and say, oh, P4, VirtIO, everything wonderful, but how do I boot? How do I manage this device in my fleet? And so the comment earlier about lifecycle management in the Red Hat session, I think is really important. It's definitely an area that we've started to try to document inside of IPDK and inside of the target abstraction interface, in fact, is to say, okay, well, and now that we have created this new device, because it gives us the nice isolation, allows us to run our applications here as opposed to on the host, all that's wonderful, but now I have a new thing I have to go and track. And update its OS, and when it has a CVE, I have to go and fix that. So this I think is a really big challenge. Certainly nothing P4 about it, but if I had to pick a place to start inside of OPI, it should be really good to see if we can get all of these devices to sort of be booted and managed and and flashed all or securely booted even in a consistent manner.
I completely agree, Dan, both with you and with Rob before. I think that P4 is great for switching, but we have plenty of other things on our plate, NVMe, IPsec, or a full F5 or Fortinet load. So these do not go well with P4. However, I completely agree with you. Management should be a very easy task, heavy lift for us to start with, not a heavy lift to start with, such as OpenBMC or tools of that nature. And if you want encrypted, Silicom is more than willing to contribute to the code that we wrote, which is microBMC, an encrypted ARM-based management system that you can run on either an ARM or an x86 or whatever you have on that card. We can contribute that gladly.
Elad, I think there's a whole thread about no vendor posts. I don't know, you should refer to the guy who's complaining about that.
Well, I can refer to myself only, but I'm saying that we.
Sorry, I couldn't help it.
That's perfectly fair. Fair shot. I would say that we'll gladly contribute the secure BMC that we've written, and it's an open source BMC. It's just a encrypted BMC that we'll gladly give, and this could be a start to that management aspect of it.
Yeah, we have a whole breakout session on Lifecycle and those sorts of topics. So yeah, let's continue that part of the conversation there, because we have Lifecycle APIs and provisioning as our third breakout session today.
And in the interest of time, we have this picture that we obviously don't have time to go through, but I think it just gives really good color. I think Marvell showed this earlier in some of the OPI session, Diamond Bluff sessions. It really shows the breadth of things to tackle here, and sort of where to start is my first question. And also, how do we make sure that we make sure that all of the different vendors and targets are represented, both software and hardware targets, just like the earlier session about being able to make sure we can continue to do all the same things that we're doing with an IPU on a regular software platform, I think is really important. So we don't want to be writing a bunch of stuff that's sort of bespoke for an IPU, but at the same time, we do have to sort of register that this is a completely different environment than what we did with SmartNIC. SmartNIC was a sort of a peripheral hanging off of the CPU, and now we've separated and isolated all of that into its own device that is now in some ways controlling parts of what's happening on the host side.
Dan, may I suggest that we follow the mindset of the ORAN consortium? They did work groups for each and every block. So for example, we can do a work group for common APIs, a work group for platform drivers, and so on.
Yep, we're already down that path. So we've already got a couple of different subgroups created for doing exactly what you're getting at.
Salut. If you fill out the Google form that we posted, the link for the OPIproject.org has a link to the Google form. I can take you through orientation, and sort of in there, we'll go through what the subgroups currently are that you can join and participate in. But we also realize that we're going to need to be spinning up more subgroups. We've just been limited so far in the amount of participants we've had. So that's one of the reasons we really need others to come join us to help drive these subgroups and make sure that we have multiple points of views represented, because we didn't want to get too far down any of these paths with very limited scope on our point of views, and we want to open it up to get more input. So you're absolutely right. That's exactly what we should be doing. We can't tackle it all as one big group. We need to divide and conquer.
Yeah. And also another great way to participate is code. I like the previous suggestion about offering up open source code. And it doesn't mean that you have to go and put it into a special OPI or IPDK GitHub. References are also highly welcomed. Also, the website that has all the recipes for IPDK is open source. So if you have a recipe or some other concept around, hey, this is how I want to do management, or this is how I want to, offload this application running on IPU, DPU, absolutely would welcome these types of concepts, making it on the open source website for IPDK. Can
I follow up on that, Dan? I think there's a super subtle and critical point there, and actually Tom Nadav touched on it too. This is a new enough space that I think there's a lot of contributions that can come from people who are not coding, contributions that are coming from people who are coding. And I think kind of the life and death and what will make this group successful or not will be kind of equally balancing those and making sure the two groups are talking, because honestly, typically they don't talk. And so almost even at a high level, IPDK has been fairly code focused, and some of the Diamond Bluff pieces have been more use case and slide focused, and trying to get those two to come together the right way. I think that's where the magic is, and something we need to continue to be careful of.
I 100% agree with you, Rob. And I loved the conversation earlier about making sure we're bringing in customer use cases and customer point of views. I'm super excited to see some of the telcos and some of the other potential users in this space here. Really want to get that use cases and customer point of view subgroup kicked off. So would love participation in that.
A quick question, Chris. Did you already invite some of the cloud vendors? So the tier 1 and tier 2 guys?
So some have been reached out to. We're still broadening and absolutely open to inviting more people.
I can talk to that more specifically. Okay. All of the top 10 cloud providers have been invited to this, and I believe most of them have come. Only a subset of them are ready to speak. So I won't out anybody for the names that I know, but we've got pretty good coverage there.
One last thing that I touched on previously yesterday on IPDK is that we've broken up the interfaces on the website between RPCs at the top that would talk to applications. Like this is the interface we use when we're having like Kubernetes offload its data plane into the IPU, or the interface that you use to go and manage the components on the device. And at the bottom, we made it a functional interface. So more like an SDK, more like something that you would see, if you had a switch device or a smart NIC device, because that was sort of the commonality that we had across our different targets that we were interacting with. Would really like feedback on whether or not this is the right sandwich, the right layers to try to define, and want feedback as to are those the right set of things? Do we choose the right pieces? Because very little of this is brand new. Most of it is curated from other open source projects like P4, like OpenConfig, and at the bottom we're using something from p4.org called the table-driven interface as a super generic kind of like interface to get to these different types of hardware and software targets.
For my 2 cents, I would say Redfish probably needs to be replaced with something else, especially if you want to encrypt it.
Yeah, and I think, one of the reasons why we like the RPCs in the top, most of them are based off of gRPC. So, that allows us to get to the security model that we want. With all of these different devices, it really is someone mentioned zero trust previously, but there really is zero trust between what's running on the IPU, DPU, and what's running on the host and what's running in the network. So you have to build that trust up over time. And, that's where that sort of redfish line there on the website is talking about, being able to manage the system without having to assume that sort of all the cores and all the functionality of that device are up and running. It's almost like a BMC function.
So Elad, what would be the alternative you would suggest to Redfish? Just curious.
I would say the part I mentioned before, which is an encrypted BMC code that can run on any of the cards. So as long as they speak the same language, it shouldn't be a problem if the code is open. So I would say that encrypting is one piece, and giving open code that could be adopted and changed would be the second thing. I think Redfish is a little bit already a little bit old, and also not open enough with the features that I'll be interested in.
Okay, I mean, that'll be an interesting contribution from your side. I think that's, and I want to echo what Dan and Elad, you said earlier, that I think that should be one of the top priorities in terms of the order in which we do things, right? So so the sooner we kick off that life cycle management and deployment side of things, I think that would go a long way in standardizing DPU IPU deployments. So no matter how right we get everything else, if we don't address that piece, I think it's going to be difficult to get it off the ground, this whole initiative. Yeah. And I had another quick question for you, Dan, about, so this P4 defined OVS, I think, is a very compelling use case. I was curious what your strategy has been so far in terms of having the P4 runtime and open config framework, developing those, that side of the equation, and having like remote SDN controllers be able to consume this new paradigm. I think that's a part I'm a little curious about.
Yeah, so P4 OVS is a really interesting conglomeration of different things. If you look at the patch set, what we're doing is, primarily we're taking some of the work that we did in Stratum, where we had P4 runtime and OpenConfig drive the device. And what happened previously is that there was a project called PINS, P4 Integrated Networking Stack, that brought those same components to Sonic. And so we took a lot of the influence of that PINS project, and we brought it to OVS because we felt that for many users, treating the IPU like a server that's running OVS is a lot more familiar than trying to treat the IPU as a switch running Sonic. And to me, to each his own, and I hope someday IPDK will give you that choice, like I want to use Sonic or I want to use OVS, or I want to use, but what we mean by OVS really is we mean the Linux kernel. So, the interesting part of P4 OVS is how we had to integrate the pieces of the Linux kernel with those pieces of Stratum, so that, if you had a packet come in and it gets trapped, we would like to be able to use some of the Linux kernel control planes to be able to do LODP or FRR or all those types of things that you would expect if you were running this IPU as a server. And so, that gives you like all three capabilities. It gives you the P4 runtime and OpenConfig stuff from Stratum. So all the kind of applications that we wrote for Stratum start to port over really nicely. It gives you the Linux integration that you would expect if you're doing things that are used to having a router running on the server. That all sort of works pretty well. And then the third part is, of course, OVS. So if you want to use OVS to do your virtual layer 2, be able to integrate with OVN, we pick those up, and at the very top, all of those become RPCs, whether it's, P4 runtime or OVS DB, or sadly, for some of the Linux kernel stuff, you end up writing a script that SSHs into the box and does some shell scripting. But at the end of the day, you're always talking with something out in the network, either, with SDN controller or distributed protocol. And we can leverage all of that existing. Don't have to go and sort of reinvent the wheel in many different places with that application interface at the top. And that's been very that's given us a leg up in terms of trying to figure out what's the best way to integrate these functions, because when we have something like P4 runtime at the top, it opens up the sort of the aperture of what you can put in that device. You're not sort of limited by sort of existing interfaces. So you can continue to use the existing interfaces that you have, but then you're like, all right, well, I want to add something a little bit extra. This is, again, the same sort of value prop of pins. I want to add that little bit of extra, or I want to add another application that sequences all this functionality inside of the pipeline, and the P4 runtime lets you do that. And P4 OVS, one of the features that we added was the ability to add multiple applications and sequence them in P4.
Makes sense.
But here I am talking about P4 again. I shouldn't do that. At the bottom, on IPDK, we've split the target abstraction into two pieces. The first piece is actually about the interface between that host on the left and the sort of the big blob on the right. Is when a really cool thing about these devices is that because they're sort of autonomous and they're separate from the host, they can now choose how they export their functionality to that host. And so, what we have defined thus far in IPDK is to say, I'm going to export BirdIO devices and NVMe devices to the host. And we're doing that in a way such that they are PCIe devices, but they look like PCIe devices when they're emulated in KVM. And so this sort of preserves all of the software layering, so we can do all the kind of accelerated IaaS type of functionality without having to use sort of the specialized SRIOV IaaS control plane stack. So yes, there's a couple extra steps to make sure you have your all of the different devices aligned, but we can continue to use the existing infrastructure that's there for BirdIO. Rob, go ahead.
Yeah, sorry. Folks might see D. Taleko pointed something. For folks who have worked with Dan and myself for the decade or so, know that he is also an Intel employee. I was trying to get him to update his things, so it actually said that, but he actually hits on a super important point that I think is worth discussing here, which is, we heard from all the talks today that there's kind of a desire to abstract away the hardware. Write once, run many, go to sleep at night with a smile on your face, right? And I think we all know that that's not really possible if you want to get performance. And that's really kind of the heart of Dan's question. And so let me kind of frame the problem differently, because I think it's super important for this discussion. Right now, we're in a world where the APIs from the hardware leak into the application and affect how you write your application. So if you want to port your application from one family of hardware to something completely different, it's basically 100% code rewrite. And like 100% is just horrible. And so you could, if you have like foresight and you kind of get your APIs layers right, then maybe you can create some application level APIs. But even that's hard. And so I think the goal for us as OPI is to create enough of a layer with enough abstraction that it's a lot less than 100%, but practically more than 0% code rewrite. And so if you look at that as a goal, as you move from one piece of hardware to another, if you move from a MEV to a Bluefield to an Octeon or what have you, I think expecting people to do 2%, 5% code rewrite to get the performance that they want, I think that's realistic. But that's to get the performance. And if you don't care about the performance, maybe get away with 0% code rewrite. But if you don't care about the performance, you probably shouldn't be running this on a DPU or an IPU anyways. So subtle question that Dan was posting, but I think one that's important for us to think about. And I don't think the goal is 0% code rewrite, because the only way to do that is really to sacrifice performance as far as I'm concerned.
Rob, can we start with something a lot more basic, and forgive my layman type of mindset on this, but can we start with indeed treating this as a server and then saying hello world, and then saying I have on this server, I have this much memory, this type of ports, this type of, let's call one block CPU, one block accelerator. And then it just comes up and says, I have all these parts. And then we give a pipe for each part, or we decide on how to talk to each part.
You know, and you, Elijah, you know my background with OpenFlow, you know my background in open networking and whatnot. I will give you what I jokingly call a proof by sour grapes, which is, you know, I've tried that really, really hard for, you know, more than a decade. And that basic level of thing usually breaks down. You know, historically, it's broken down in the OpenFlow 1.1 era or in the Open Daylight side. You know, it turns out that the way that things connect, the metadata that gets passed from point to point, the use cases that a specific piece of hardware is developed for, they really do matter. And you know, while I agree, you should be able to just list the components and let people kind of cobble together the way that they want. At the end of the day, I mean, there's real silicon that connects these things in certain places. And the more you kind of hide that from people, the harder it is to actually achieve the use case that the thing was meant for with a bunch of layers of abstraction along the way. It is my opinion. But it's the reason why I said what I said is not to say that we shouldn't try, but I want to make sure that there's kind of a realistic bar for success, if that makes sense.
But Rob, doesn't it mean that we have two layers maybe, right? One layer is really the infrastructure and components, and then you are talking about another layer that can be built that's more of how they can get connected, and then how
I guess what I would say is I think the best APIs that I have seen are really a bunch of layers. And you know, as you come down the layer, really what you're saying is I'm willing to trade off more work for more performance. So if you work at the highest layer, you can get kind of like, for the least amount of work, you can get kind of mediocre performance. And you know, maybe that's where Elad is talking. And you know, for the next layer down, you do a little bit more work and get a little bit more performance. And just to throw it out there, I mean, no matter how successful what we're doing is here, if somebody has, you know, needs the absolute last bit of performance, they're going to bypass all of this, bypass the vendor provided SDK and work directly with the registers. And I think that's the reality. And so thinking of it not as necessarily one layer or two layer, but really an N layer solution where there's kind of this trade-off that I'm talking about, at least that's the design pattern that I've seen be successful in the past.
I do have one quick comment, Rob, following up on that. There might be something in the middle. I'm not sure there's a line between what you were just saying, but for example, think about vendor extensions within OpenFlow and within OVS. That was part of the framework that allowed some extensions. I'm not arguing that that's a solution to this problem. I'm throwing it out as something that was introduced into the framework, which may have improved things and may have made things worse. But we probably want to be looking at that and figuring out how those things fit together for this question.
I wish Ben Pfaff was still on. It'd be great for the three of us to have this conversation, but I agreed.
So my last slide here was sort of how we get organized. And I do like the organization we have where we have, you know, the breakouts today are a breakout about targets, a breakout about applications, and a breakout about lifecycle management. I think that that's probably a pretty good place to start. And so, you know, as we you know, wrap up today, I hope we can come back to this question now that we're out of time in this breakout, to be able to say, all right, what's our next steps, and how do we, now that we all know that we all have interest and, you know, want to work on this together, you know, how do we put the right sort of communications in place so that we can work on this together?
Thank you, Dan, Nadav, and Liron. I think this was a very vibrant conversation, and obviously there's a lot we can do with this conversation as we organize OPI.